Hey guys, hopefully things are still going well. Again, we're going to move into the mechanisms part of this. So we're going to start talking about how reactions actually happen and why we need to look at what is the pathway for that particular reaction rather than just assuming that we know what that pathway is. Because in order for us to be able to determine a rate law, we need to know what that pathway is. And we'll talk about why that's the truth. All right, let me go ahead and share my screen so we can get some idea what we're talking about. And let's go ahead and start talking about mechanisms. So questions, comments, problems, again, if you have any whatsoever, please let me know. Email, phone, drop by my office hours, any of that. As soon as I get all of these lectures posted, I will work on getting some practice for exam 3. I'm going to do the practice for exam 3 before I do the practice for each individual lecture, because I think it's more important that we talk about how those things may come together on an exam rather than each individual component. So that's what I'm planning on doing. All right, let's move forward. So here we're going to be talking about chapter 13. This is sections 4, 5, and 6. So we're going to talk about activation energy and temperature dependence of rate constants. Then reaction mechanisms, i.e. what is the pathway to get from reactant to product. And then we'll talk about catalysis. All right, we talked about catalysts before a little bit in terms of what they do with reaction rates. So we'll talk about that a little bit more here, okay? Now, when we talk about this, the first thing we need to talk about is how do reactions happen? Well, reactions happen using the kinetic molecular theory of gases. Now, what happens in the gas phase is almost exactly the same as what happens in the liquid and the solid phase. It just happens a lot faster in the gas phase, and therefore it's easier for us to describe. So we make a couple of assumptions when we talk about the gas phase. We assume that gas is composed of molecules that are separated by distances bigger than their dimensions. Gases are in constant motion in random directions, that they often collide with each other, and that gas molecules are not attracted to or repulsed from other gas molecules. The kinetic energy of the gas particles is directly proportional to the temperature of the gas. Chemical reactions are the result of collisions of molecules, but it's not just related to the collisions, okay? Not all collisions have sufficient energy to result in reaction. There is a minimum energy that's required for that reaction to take place, and that's called the activation energy. We'll talk about that in a couple of minutes. One of the other things is it needs to be in the correct orientation, okay? So we can talk about this in terms of, I can't park my car in my garage if my garage goes this direction. I can't park my car this way. So that's the wrong orientation. We have similar things that need to happen when we're talking about reactions. Okay, the molecules need to come together in a way that will be conducive to the reaction that we're trying to make. Okay. So let's talk about activation energies, also called, which is related to something called the transition state. All right. So let's look at that. So you'll see that we have an energy for A and B, which is where we start. Okay. And I'm going to grab a laser pointer. So we start with A and B. Over here is the reactants. We see that there is an amount of energy that's required to go from A to B before we get to C and D. Now, overall, we give up energy in this particular process, okay? So this is an exothermic reaction, so it gives up energy to the universe. It's fabulous. But we have to put in a certain amount of energy, this EA, to get from reactant to this activation energy, okay? Now, the high point is the transition state, this AB, I think you call it double star. I can't remember what the terminology is for that line with the two crosses across. But that's our transition state, okay? It doesn't exist for very long. It is somewhere in between reactants and products. It's not something that we can actually measure per se, but that's our transition state. We know that there's an energy associated with getting from reactant to transition state and then to product. we can see that there's a similar process that happens when we start with A and B down here, and then we have to get to that activation energy to have C and D up here. Now, this requires energy to be put in to make this reaction happen. So I need to add energy to this. This is an endothermic reaction, so it requires energy from the universe to make this work. And that EA is much larger in this case because it is necessary to get that much more energy added to it to make this happen. Okay. So EA is our activation energy. AB up here, this is our transition state. We start with our reactants, A plus B, and our product, C plus D. The difference between A and B and C and D is the enthalpy of that reaction. Okay, so that's the energy associated with that particular change. Right? So that's that. Now, you need to be able to describe what all of these things are. You may be asked to label one of these graphs. You may be asked to look at one of these graphs and tell me, is this exothermic? Is this endothermic? What is the activation energy? If there are values given to you for this, that kind of stuff. That's the expectation for those, is so that you can interpret those graphs. Now, let's move to our next slide. The Arrhenius equation. K equals A times E to the negative EA over RT. EA is the activation energy. R is the gas constant, 8.314 joules per Kelvin mole. T is the absolute temperature, so the temperature in Kelvin. A is a representation of the frequency factor. It's related to how often the collisions result in products. Okay, and that's specific for a particular type of reaction at a particular set of conditions. The rate constant, K, decreases with increasing activation energy. So the more energy it takes to get from reactant to product, the less that rate constant is going to be. So it increases with the increasing temperature. Another form of this equation is ln of K equals ln of A minus EA over RT. This equation is a good one to use, as it's in the y equals mx plus b format. So if I plot ln of k versus 1 over t, that'll give me a straight line with a slope of negative EA over r, and the intercept with the y-axis is a. Okay, so that's something that we can talk about, and we're going to see that on the next slide. If I can get it. Yay! So here's my raw data, temperature in degrees C. This is my rate constant in 1 over moles per second. Okay, this is my process data. So I've taken 1 over T, with the T's been converted to Kelvin, and the natural log of K. So I've plotted natural log of K versus 1 over T. I can see that this line has a line of best fit of 0.9998 is my R-squared value, so it's a pretty good fit. I can see that my slope is not negative 9253, and my intercept is 24.504. So I have EA equals negative 3.14 joules per mole times Kelvin times negative 9253K equals 77,000 joules per mole. And we use the slope as the T to solve for EA. Okay, so we've solved for EA here. Okay, so that's my activation energy. Yahoo! I was able to use this graph to do that. And that's something you should be able to do as well. Questions, comments, problems on that? All right. Well, that's how we're going to see that part of it. Okay. So that's how we're going to look at the Arrhenius equation. That's how we're going to look at the temperature dependence and what the activation energy is. Okay. Activation energy, transition states, whether it's exothermic or endothermic based on the plot. Looking at a plot of ln of Ka concentration, the natural log of concentration versus natural log of K. Yeah, natural log of the rate constant versus 1 over T. So that'll give us the ability to solve for EA. that. And like I said, you will get practice on doing that when I get those practices put up for you. Now, reaction mechanisms. Very few reactions happen in a single step. And I'm going to give you an analogy for this. I mean, let's think about this. I can tell you, okay, I got to work, right? When I go to work, I have to get out of bed, take a shower, get dressed, get in my car, drive to work, stop on the way to get, the stuff that I take to work with me every day. All of those things have to happen before I get from my bed to where I work. All of those things are part of the path that I take between the bed and where I work. So that's my mechanism for getting from A to B, right? From bed to work. And it depends on what I'm doing, where the slowest part of that is, all right? It could be that on a particular day, the slowest part of that is me getting out of bed. It could be on a particular day that the slowest part of that is me stopping at the Sphinx to get something because there's 8,000 other people in the line with me. It could be that the slowest part of my day is getting out of the parking lot at the Sphinx because I got hit by somebody else while I was there. All of these things happen, okay? So my pathway is not dependent on where I start and where I end. It's more dependent on what happens in between, okay? And that's what we mean by talking about the mechanism, all right? So my mechanism is going to determine what my rate law is because it's going to determine what the steps are that I take between my starting point and my ending point, okay? So if we look at a potential energy versus reaction progress graph, similar to what we looked at before, we go from reactants to products. Again, our reactants to products, we give off energy in doing that. So that's an exothermic process that I'm looking at here, right? I know that this high point in this first graph, step 1, is measured by the activation energy for that particular compound. And then I have an intermediate that exists at that top point. Okay, we talked about that last time. But I also know that this particular pathway has 2 steps because there are 2 humps in that graph. So it's a 2-step process. That first step has a much higher activation energy than the second step does. So I would expect that that is the bigger barrier to getting from reactants to products because it's the one that requires the most energy, okay? In between the reactant and the product, I have this low point. What exists here is what's called an intermediate, okay? So an intermediate is something that is a stable compound that we can isolate. Remember, I said that a transition state is not something that we can isolate. We can't look at that particular thing as it exists. But I can look at an intermediate. I can isolate it. I can, as that one step is done, I can collect the product from that and take a look at that. Okay, so that's an intermediate, and that's the difference between that and a transition state. Okay, intermediates are species that appear as part of the mechanism, but they're not a part of the overall final reaction, and that's because they're made in one step and then consumed in the next. So they're not part of that overall reaction, but they are an important part of getting me from point A to point B. All right. So our proposed mechanism will allow us to measure the intermediates that are formed. The molecularity of a reaction is the number of molecules in an elementary step. So a bimolecular reaction has 2 molecules that are required. A termolecular reaction has 3 molecules that are required for the elementary step, and those are very rare. Okay, it always has to be more than 1 molecule, unless that molecule is decomposing. All right, if it's the decomposition of 1 molecule into more than 1, then it's only that one thing that we made. Okay, so rate laws and elementary steps. So now that I know that I have multiple steps that are involved in this particular reactant to product process, all right, and there's an intermediate in the middle that I can measure, that I can collect and measure, then I know that that's a 2-step mechanism, okay? I also know that the elementary step is that energy associated with the first part. So this hump right here is associated with the first elementary step. This hump right here is associated with the second elementary step. So there are 2 elementary steps that are required to get me from reactant to product. Okay. The reaction order for each reactant in an elementary reaction is equal to its stoichiometric coefficient in the chemical equation for that step. So when we're talking about elementary steps, if I have A going to products, the rate law for that is the rate constant times the concentration of A for that elementary step. Now, this is not for an overall reaction. This is just for an elementary step. If I have A plus B going to products, my rate is equal to K times A times B. If I have A plus A as my elementary step going to products, that rate is equal to K times A squared. The rate determining step means that we have one particular step that's a lot slower than the rest of them. And if I look at that one, then that reaction is the one that's going to tell me what the overall rate law is. And so if I can use the stoichiometric coefficients for that chemical reaction, that particular elementary step, to look at what that rate is, and for the slow step, that should equal the rate that I have for the overall process. Okay. Since we know that overall reactions occur in many elementary steps, the one step that is the slowest determines how fast a product is made. That's my rate determining step. And again, while that varies for me in the morning, it doesn't really vary when we talk about how these things actually occur. All right. The sum of the elementary steps must give the overall balanced equation. All right. And the rate determining step should predict the same rate law that is determined experimentally. All right. If we choose a rate determining step that does not have the same rate law as we determined experimentally, we picked the wrong step. Okay. So that's how we look at that. Now, experimental data and determining rates. So we can look at hydrogen peroxide decomposition. The overall reaction for this is 2H2O2 aqueous goes to 2H2O plus O2. The experimental rate law, rate equals K times H2O2 times I minus. I minus? What the heck? I minus is not in this overall reaction. So what does that tell me? Well, what it tells me, because I've been paying attention to everything that we've been talking about, is that I minus is an intermediate that is necessary to get me from 2 H2O2s to 2 H2Os plus O2. So that I minus matters. All right. The overall reaction has to take place by more than one elementary step, which involves that I minus, since I minus is present in the rate law, but not in the overall reaction. So I can look at step 1 as I2 with a K going to 2I, right? So it breaks those 2 I's apart. And there's a K for the forward reaction and a K for the reverse reaction. I know that this becomes an equilibrium and the rate forward is equal to the rate reverse, Okay, and that's what we look at in this step right here. So reactant to this transition state then comes to my intermediate. Okay, my 2I, that's my intermediate, right? Then I have H2 plus 2I gives me 2HI, all right, for this particular reaction. And the I atoms are the intermediates here, all right? So here I have H2 plus the 2I going to 2HI, and that gives me that particular, the I as the intermediate, okay? Does that make sense? Hopefully that makes sense. Questions, comments, problems about that? All right. Well, then let's keep going. Last thing we're going to talk about with this particular topic is catalysis. All right, you may have heard of catalysts. catalytic converters. You may have heard of catalysts in terms of biological reactions. A catalyst is a substance that increases the rate of the reaction by lowering the activation energy. The catalyst does not affect the position of the equilibrium, so it doesn't change how much product I make, how much reactant I make. So if they ask you, I have a catalyst for this, how does that change the value of K? It doesn't. All right, we talked about that before. I said we'd come back to it. The catalyst doesn't have anything to do with where that equilibrium lies. It only has to do with how much energy it takes to get me from reactant to product. All right. So it can be a heterogeneous catalyst, meaning that's in a different phase than the reactants, or homogeneous in the same phase, right? And enzymes are a form of catalyst, okay? So again, the only thing that catalyst does is lower that activation energy. The catalyst is not consumed in this process, all right? It is given back to us. And all it does is lower that activation energy. So, questions, comments, problems. How might you see this information on the test? Well, what effect does the catalyst have on the equilibrium constant? That's something you might get asked. What does a catalyst do? I.e., what is its purpose? What is the substance? What does it mean to have a catalyst? If I show you these two graphs and I ask you what the difference is between these two situations, you should be able to tell me that this second one, the one on the right, has a catalyst and the first one does not. Okay? Those are things that I would expect you to be able to do when talking about catalysts. Okay? Questions, comments, problems? Hopefully not. That takes us through everything that we're going to talk about in terms of mechanisms and catalysts. All right. Again, I will get together a practice sheet for you guys so that you can see what kinds of questions you can expect about catalysts and reaction rates and all the rest of this once we're done with all of the lectures. All right. Hopefully you guys are okay with that. If you're not, please let me know. I'm going to go ahead and stop sharing and I'm going to stop recording. So I will see you again soon. Thanks, guys.